Carving a pumpkin with chemistry.
It can be a little bit loud, not like hydrogen oxygen balloon loud, but it can be a little bit loud. I scared the crap out of some little kids on Thursday and lost half my audience because I forgot to tell them it was loud. So now I'm just stalling, waiting for the gas to build up. Everybody have a good view? Oh, shoot. Sorry, just 1 second, let me get a little bit more. Go big or go home is my motto. Alright, this is going to be real interesting. This can either be amazing or I'm going to burn my hand off. Alright, let's go for this. Okay, I'm going to try it, and if not, we're going to carve a new one, and I'll bring it out to you guys, all right? 1, 2, 3.
Exciting. So that was using chemistry. That's like applied chemistry, using chemistry to carve a pumpkin. In case you're curious, that was calcium carbide. I guess we should spend at least 2 seconds talking about the actual chemistry that was going on within that balloon. So what was going on is we had calcium carbide, which is CaC2. Carbide is C2 2 minus. So calcium carbide, calcium 2 plus, C2 2 minus for the carbide ion. What's going on is this is reacting with water, so we're putting solid calcium carbide into water. The carbide ion was reacting with water, pulling H pluses off water. If we react 2 water molecules with calcium carbide in liquid water, what we end up forming is H2C2 gas, acetylene. So we make acetylene gas, which bubbles away, builds up within the pumpkin, and then calcium hydroxide is what happens with the calcium and the oxygen. The OH minus ion afterwards pairs up with calcium, water-soluble compound from chapter 4. So we actually have like an acid-base reaction going on. We just have the calcium carbide acting like the base, water acting like the acid, making this combustible gas, and then builds up in the pumpkin, and then we detonate it, and boom. And what happened at first was the top of the pumpkin had fallen into the pumpkin. So it broke the seal, and just too much air got in for it to burn on that first try. So pretty neat. So using chemistry to help carve a pumpkin. And I think we got that video, so you can watch it again if you, it might be kind of interesting to see that again. That was a pretty big flame. Okay, so our opening question today, let's actually let me take a peek and see how many people have answered this. Let me give you guys 1 more minute to wrap this question up, and we'll go through this one on calculating the formal charge from this Lewis structure. right, let's take a look at this one here. So the idea of formal charge. So formal charge is the charge we can calculate if we assume that bonds are equally sharing their electrons. And so what that would mean, if we look at each of these bonds, we can think there's 2 electrons being shared within each of the single bonds, and that one of the electrons is closer to iodine and one's closer to chlorine in each of the bonds. So then if we look at chlorine, you can kind of think of isolating in a box, if you will. You end up with the structure for chlorine that has 3 sets of lone pairs and then an extra electron. What you're trying to evaluate is what's the charge for that many electrons surrounding a chlorine atom. Chlorine has 7 valence electrons, meaning if it has 7 electrons surrounding it, it would have a 0 net charge. So the formal charge of the chlorines here are all 0. So uncharged chlorine atoms. And then the iodine, we could calculate it, like we could look and say, okay, iodine should have 7 valence electrons surrounding it, and if it did so, it would have a 0 charge, and it's actually surrounded by 8 electrons. It's surrounded by the 4 electrons from the non-bonding electrons, and then it's surrounded by half of the 8 bonding electrons. So if you think of each bonding electrons as being 2, 4, 6, 8 total bonding electrons, this is our number of bonding electrons. Cutting those in half, that's just cutting each of the covalent bonds in half. You could also draw a box around iodine and just do 7 minus 8 for minus 1. So a few different ways you can think of calculating this, but the whole idea is just looking at the electrons surrounding a particular atom, compare that electron count to the count that makes the atom have a neutral charge. Try to assess if it has more electrons than what a neutral atom would have or fewer electrons than what would give the atom a neutral charge. So this is iodine with a minus 1 charge. So now the formal charge is, again, it's the charge an atom would bear if those covalent bonds are perfectly equally shared. Now, what do you think the actual charge would be for the chlorine atoms in a real molecule of ICl4 minus? Like, do you think there'll be 0? Do you think there'll be plus some positive charge, minus some partial charge? What do you guys think? The actual charge of the chlorines are probably partial negative, right? Because chlorine's more electronegative. It's going to fight for those bonding pair electrons more than the iodine atom will. So the actual charge of the chlorine atoms is probably partially negatively charged because the formal charge is 0. So in the Lewis structure, equal sharing of the bonding pair electrons shows 0 charge. So then when you say, okay, now think about chlorine versus iodine, which one's going to fight for the bonding pair more? Chlorine's going to win the tug of war. So it's going to pick up a small partial negative charge. By partial charge, we mean if it were fully ionic, it would be minus 1 electron. So it's somewhere between 0 and minus 1 electron. So it's probably like minus 0.1 electron charge units to minus 0.2 electron charge units, somewhere in that neighborhood. And so then the formal charge, iodine, minus 1. Now, one other thing you can see is that you should be able to sum up all the formal charges of each of the atoms and calculate the overall charge. So like we see here that the ICl4 is noted to be an anion. It has a minus 1 overall charge. So if we take the chlorine's formal charges all sum up to 0 plus the minus 1 formal charge of iodine, we get the minus 1 overall formal charge to calculate. So you do have a check. Once you assign your formal charges, you could go back through, add them all up, make sure you get the charge on the molecule. If it's uncharged, it should be 0. If it's an ion, it should equal the charge on the ion. Okay, we're going to pretty much spend the whole day today doing different types of Lewis structures, so we'll get a lot of experience calculating formal charges, comparing, and double checking. So let's go through and look at our rules for Lewis structures. We were getting into some of these last time, like summing up the valence electrons. Let's use carbon tetrachloride, CCl4, for our first example today. So we want to sum up the valence count. Hopefully that's pretty straightforward. That's one of the big ideas of chapter 6, is seeing that carbon has 4 valence electrons. Chlorines, the entire halogen group has 7, so there's 4 of them. So that's a total of 32 valence electrons. So the key, we're adding up the valence because they're the outermost electrons. The inner core electrons are too close to the nuclei of their atoms. They're not going to interact with each other when we're making bonds between different atoms. So the outer valence electrons are the largest orbitals. They're the ones that are going to participate in bonding. So then we want to locate the central atom. Pretty easy here, because usually it's the first atom. listed. If it's like H2O, then you know the hydrogens are going to connect to water. Hydrogen only forms one bond, so hydrogen's not going to bridge between two different atoms. So we just have to have a little bit of thought sometimes for locating that central atom, but usually it's that first one. It's usually not so hard to locate the central atom, but we'll try to pay attention in examples to point out why it is. We might know in some more complicated examples which one is supposed to be the central atom. So central atom, attach the other atoms to it. Complete the non-central atom octets with lone pairs. And then count our electrons. So the key here is we're doing non-central atom octets. Like if we didn't have an octet on carbon, we wouldn't start adding lone pairs. We have to count our electrons up before we start adding lone pairs to the central atom. There's 8 electrons per chlorine, 4 chlorines, so there's no electrons left over. So there's 0 lone pairs to go on carbon, which is good because carbon's actually satisfying the octet rule right now. We'll see some examples where we want to be careful when we put lone pairs on the central atom, but we'll put lone pairs when there's electrons left over here onto the central atom. Why the central atom then? Well, we'll see in some examples, but it'll be because the outer atoms already have their octets filled. There's nowhere else on the outer atoms to put electron pairs, so if there were leftover electrons, they would go on the central atom. And so if not enough electrons, like if we had used too many electrons at this point, we'd have to start making multiple bonds. So if we found that we only had 30 electrons and we've used 32, then we'd have to put a double bond somewhere. We'd have to think about where we might put that double bond. So we'll see that used in some other type of molecules. So the last thing we might do is just double check our formal charges. That's usually a check. A lot of compounds will show 0 formal charges across the molecule. The formal charge of carbon, 4, gives it a count of a 0 charge, 4 electrons surrounding carbon. It has 4 electrons surrounding it. So the formal charge on carbon is 0. The formal charge on the chlorine, 7 minus 7, they're also 0. So 0 formal charges around. Sometimes we'll have some molecules where we have to do some things to minimize formal charges. We'll point some of those situations out as we go along. So let's do ICl4 minus next. Actually, see if we could come up with that Lewis structure that we just had on the previous slide. So for ICl4 minus, now iodine, again, like back in chapter 6, when we were counting valence electrons, we said the D subshell doesn't count once you fill it. Like iodine, at one point you may have thought it should have 17 valence electrons. That would lead to a pretty complicated Lewis structure if we had to somehow count 17 electrons for iodine, but it's only 7 because the filled D subshell doesn't really participate in bonding. It's really close. The D electrons are much closer to the nucleus than the outer p orbitals and s orbitals. So 7 valence electrons for iodine, of course 7 times 4 for the chlorines. The charge, you got to pick up an electron for the minus charge. If we have a positive charge, we'll see in NH4+, we take an electron away. So for ICl4 minus, we come up with a total of 36 electrons. And so then for our Lewis structure, central iodine, I think it's pretty obvious that's our central atom. Most compounds, it's pretty obvious which atom is the central atom. The chlorines attach the central atom, complete their octets. So of course that's only 32 electrons. 4 electrons left over onto the iodine atom. And so that's how we can get to the Lewis structure that we had in that opening example, just making sure that we could actually, from a formula of ICl4 minus, actually arrive very easily and systematically at that particular structure. NH4 plus. The big thing with ammonium is dealing with the positive charge, just to make sure we see that with the positive charge, we take the valence count from nitrogen, which is 5, 4 times 1 for the hydrogens, and then minus 1 for the charge, being plus 1. So the plus charge removes one of the outer valence electrons from the molecule. So we only have 8 total valence electrons. So central nitrogen, hydrogens. Now the hydrogens don't obviously get 8 electrons each. They're happy with 2 electrons. That's the count of helium. So 2 is the stable count for hydrogen. And so then this would be our best Lewis structure. Now, usually what we want to write within a Lewis structure are showing the non-zero formal charges. Like on the ICl4-, like we calculated in the previous example, iodine should have 7 valence electrons for a neutral charge. It has 8 electrons surrounding it, so it has the -1 formal charge. And nitrogen should have 5 electrons for a 0 charge, and it's only being surrounded by 4 electrons. So if we cut the bonds in half, so the formal charge on nitrogen is +1 in ammonium. So again, we could think the actual charges versus formal charges, but for the most part within your Lewis structures, you're just showing formal charges. The formal charges are meant to give you an idea to think, okay, now where do you expect the charges to go from there? Like nitrogen's more electronegative than hydrogen. Like NOFCl, those are the most electronegative atoms on the periodic table. So nitrogen's going to fight for more electrons and pull the bonding pair electrons towards itself. The bond dipoles are going to point inward. So hydrogen's going to actually end up with a partial positive. The actual charge on nitrogen won't quite be +1. It'll be a little bit lower than +1 due to picking up some extra electrons from the bond pairs shading closer towards the nitrogen atom. So the idea of formal charge is it gives us a way to look at a Lewis structure, assume the bonding pairs are being equally shared, and then kind of let go of that assumption and think about where the electrons are going to go. They're going to head closer towards that more electronegative atom in the real molecule. So if we're thinking actual charges in NH4+, probably the hydrogen's partial positive, and the nitrogen will still be partial positive, but not quite +1. So it'll be a little bit lower than +1. So that's our opening example. Talk about that. So let's do a couple other, we're going to do plenty of examples today, but C2H4. So how do we deal with compounds that have like multiple central atoms? Like when we see C2H4, the first thing that enters my head is that the hydrogens aren't going to bridge the atoms. So if I have 2 carbons, they're going to have to somehow be connected together. Okay? And then the hydrogen's connected to them. So minimally, we kind of begin here with single bonds and then kind of go from there. The H's are the outer non-central atoms, and this molecule just has 2 central atoms. So we just have 2 central atoms. Now, I don't ever add like lone pairs onto the central atom. Like that's not part of the Lewis structure rules, is just putting lone pairs of electrons on the central atoms. We do that for non-central atoms, for the outer atoms, but never for the central atom. Because what I have to think about here is how many electrons do I have available, like 2 times 4 for carbon, plus the 4 hydrogens times 1 each. That gives me a total of 12 electrons for 8 plus 4. And so I've distributed 2, 4, 6, 8, 10 electrons. So I've only distributed 10 electrons. Now what do I do here? So I have 2 electrons left over. Like I could put a lone pair, because the rule says if you have leftover electrons, add them as a lone pair. But if I do 1 lone pair, then what about the other atom? The other atom has a positive charge, the other atom has a negative charge. So the formal charge here would be plus, the formal charge here would be negative. I could obviously fix that by using a double bond instead. So if I use a double bond, then I give each of the carbons 4 bonds. I give each of the carbon 4 electrons surrounding them. They each have a 0 formal charge now, and the same thing for hydrogen. So the formal charge on hydrogens are all 0, and likewise for carbon. Okay, so I'm going to use a multiple bond in this case because that's the way I can distribute the charge equally across the 2 atoms, minimize the magnitudes of their formal charge. So the formal charges being 0 on carbon are better than -1 and +1. What about ClF3? So pretty easy for the valence count, 7 times 4. Sorry, my like mute button doesn't work, and my phone always unmutes itself. So I'll move. So okay, ClF3, 7 times 4, 28 valence electrons. So central chlorine, the fluorines, lone pairs to the fluorines. Now, the big key idea here is we're not necessarily doing a lone pair on chlorine just yet. We're counting our electrons used. There's 8 per fluorine. There's 3 fluorines, so that's 24 total. The 4 leftover electrons then go on to chlorine. So we'd be adding 2 pairs of electrons. Okay, so formal charges. Chlorine should have 7 valence electrons, and it's surrounded by the 4 non-bonding electrons, and then 5, 6, 7. So formal charges all around are 0. All right, why don't you guys try BrO3 minus? So work with your partners or neighbors or whatever and try to come up with the Lewis structure for bromate. More in which case, the first one or the second one, or just in general? We'll go over that with bromate, because it actually kind of comes up with bromate. Okay, so let's look back at ClF3 for a minute. Notice chlorine here has an expanded octet. So in ClF3, notice how chlorine's surrounded by 2, 4, 6, 8, 10 electrons. So chlorine's actually violating the octet rule. Now, at first glance, you may say, well, is that okay? You know, which atom would we rather violate the octet rule? Now, you might think about making like double bonds. Like, do you want to do this? Like, what's so bad about this? Well, one thing that's bad with that is now we have 2 atoms violating the octet rule. So now we have 2 atoms somehow trying to pack more electrons into their valence shell. Like, you recall how neon has such a high electron affinity that it's never going to neon minus. So how could we go to like F minus here and pick up more electrons onto fluorine while also expanding the octet and somehow placing electrons extra into the chlorine atom? Like, so this seems like a bad idea. What this is doing is it's changing the formal charges in such a way that it's like maximizing formal charge. So we don't want to make double bonds to expand octets of atoms unnecessarily. So double bonds where it causes some atom to expand its octet. In fact, there's almost like a golden rule that the second row and first row elements like never expand their octets in molecules. Like when we see these octet rule violations, it's going to be when the central atom is in the third row. So like if you replace this chlorine with like oxygen, that type of compound just doesn't exist. Whereas second row atoms expanding their octet, fitting 10 electrons around that central atom just doesn't seem to work until we come up with a relatively large atom. Now another artifact on why these types of compounds exist like ClF3, is that the fluorine's electronegative. It's actually pulling electrons off of chlorine. So if you think of these types of compounds, they tend to exist when you have a relatively big central atom, so it's not very electronegative, and then you have a really electronegative atom connected to it to pull the bonding pair electrons off the atom to almost make room for those extra lone pair electrons. So the electronic nature of fluorine in these types of compounds with expanded octets, it's really common we see F and O in these examples because they can pull the bonding pair electrons off the central atom and kind of create room for that central atom to expand its octet. So one of the best ways to think of the octet of ClF3 is that in the Lewis structure, the chlorine atom expands its octet. To really examine if chlorine in a real molecule of ClF3 expands its octet, we'd have to know the actual charge of chlorine. Because I bet you the charge of chlorine there ends up being about +2, meaning that you have the fluorine atoms pulling the electrons off the chlorine atom, creating room for the extra 2. So the real molecule likely isn't expanding its octet. It's finding ways to pull electrons with the fluorine atoms off the central atom, make room for those lone pair electrons. That also then feeds into why it is the central atom gets the extra lone pairs, is because the outer atoms can pull the bonding pair electrons off the central atom, and then the extra lone pairs can reside on that central atom. So now looking towards bromate, BrO3 minus, if you're doing the Lewis structure, you might have started single bonds, complete the octets of the oxygens. That's 24 of the 26 electrons. We have an extra 2 left over to go as lone pairs onto the bromine. So then another slightly different issue arises, which is, should we use a double bond here? Meaning, should I take actually one of these electron pairs and make a double bond? So that structure would look like this one. And this is an actually tricky problem. This is a problem that silly chemists like to fight over which one of these two structures is a better Lewis structure. Because there's like two almost like rules in your head you can be thinking. One is the octet rule says atoms should have 8 electrons surrounding them. And in this structure here, we satisfy the octet rule. So the octet rule is satisfied by all the atoms. That's not true in this structure here. Bromine is expanding its octet, now has 10 electrons surrounding it. But it actually reduces the magnitudes of the formal charge, which is almost like another rule. There's this like formal charge rule. We'll see how it's used in a few different types of compounds and some other examples. But the formal charge of oxygen in the double bonded oxygen is 0, 6 minus 6 for 0. Bromine's formal charge would be 7 minus 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. For plus. Now, if you compare those formal charges to the octet rule satisfying Lewis structure, the oxygens are all -1 because they're all 6 electrons for a 0 charge surrounded by 7 electrons for a -1 overall formal charge. Bromine's formal charge is then +2. You can tell it's +2 because -1, -1, -1 plus 2 equals the charge on the ion. So by the formal charges summing up, we should get +2. And then by actually calculating it by thinking the valence count of bromine should be 7 for a 0 charge, and then 1, 2, 3, 4, 5 electrons surrounding it. So we can calculate the +2. We can double check that all the formal charges sum up to -1, the charge on that ion. Okay, so we're reducing the magnitudes of formal charge, so we're like satisfying what's sometimes called the formal charge rule. And the textbook doesn't quite lead to a definitive answer of which Lewis structure is better. So what the book would have you say is that the left structure satisfies the octet rule, the right structure satisfies the formal charge rule. So you'll see some test questions like last autumn 17 practice midterm, the spring 18 practice midterm. Well, you'll see some exam questions that say which Lewis structure for like a compound satisfying the formal charge rule, where you have to satisfy the formal charge rule and go with the structure that looks more like the left structure. In fact, you could do it one more time. Like you could make one more double bond, make a second double bond, so the electron pair moves in to make a double bond. Then the formal charge of bromine drops now to be 0. The formal charge of that oxygen is now 0. So we're like lowering the magnitudes of formal charge through double bonds, So the formal charge rule, best Lewis structure for bromate would have 2 double bonds, 1 single bond. And then the octet rule Lewis structure being satisfied would lead to 3 single bonds with a lone pair. Now, I think the octet rule one's generally the better one, I think. Like our textbook just a little bit weak and doesn't want to make that claim definitively. It argues in a particular example that theoretical, like quantum mechanical calculations seem to support the octet rule. So octet rule is probably closer to the structures that the real molecule adopts. There's an issue of something we call resonance that's really important. Like when we start thinking double bonds shorter than single bonds, there's actually a bit of an issue that all the bond lengths in bromate are truly equal. Okay, so now that might make you think, okay, the double bond one is wrong, right? Because 2 should be shorter, 1 should be longer. Once you kind of go back to the idea, remember how double bonds are usually shorter with the extra electrons than single. But there's an idea of resonance, that whenever we have a molecule that we could have drawn those double bonds on the other oxygen and left the other one single, that the real molecule could resonate even if it has an imbalance in the number of bonds. We'll look at a couple cases of resonance where we could imagine that either one of these 2 structures should lead us to predict that the bond lengths in the BRO, all 3 of the bond lengths are equal. That's a pretty weird idea at first, but we're going to look at some examples a little bit later today, have a couple images to support that idea. So if we go with all 3 double bonds here, the bromine charge would go to minus. So if we go with double bond here, double bond here, double bond here, so 3 equivalent double bonds, and then still our lone pair. So calculate the formal charge on bromine. Now it would be 7 for a 0 charge, minus 1, 2, 3, 4, 5, 6, 7, 8. So that would make the bromine charge minus, and then the oxygen's all 0. Now the issue there would be compared to this structure, we'd be now maximizing formal charges. So the formal charge rule, or the formal charge idea would say, choose the Lewis structure that minimizes the magnitudes of formal charge. Once you hit 0 on that central bromine, that's obviously as low as the charge can get. So that's why we would stop for this particular Lewis structure at 2 double bonds to satisfy minimizing the magnitudes of formal charge. Yeah, so these are covalent bonds. So which Lewis structure? So for the octet rule here, so now something to think about here is which atom's more electronegative, bromine or oxygen? So oxygen is more electronegative. If you think about a real molecule of bromate ion, we would expect oxygen to be negatively charged, and we would expect bromine to be somehow positively charged, right? Just with the idea of, like, even if we go to this, the best formal charge picture, like if you go to the double bond, 2 double bonds and a single, that bromine's not going to be able to fight for those bonding pair electrons as much as oxygen. So oxygen's going to go back to reverting to a negative charge anyways. So one of the interesting things with the octet rule structure is it kind of stops with the structure keeping the negative charge and the atoms that are actually more electronegative and probably more indicative of the actual charges of the real atoms in a real molecule. You know, so the octet rule structure, I think, leads the bonds to all looking like they're the same type. They're all single bonds. They're all obviously the same length. All the oxygens have the exact same charge. Once we get to resonance, we're going to see that even with resonance, that would be the prediction for the structure with 2 double bonds and a single. So let's come back to resonance so that we can make sure we see why that's the case. But the charges on the oxygen should be negative because it's more electronegative than bromine, and probably not 0 in terms of formal charge of oxygen. Now, if you were asking why would oxygen have 7 electrons surrounding it versus 6, that just is a relative count of, that just depends on the Lewis structure, right? This just depends if oxygen has a single bond versus a double bond. And oxygen, if it has a single bond, just picks up a net negative formal charge. So, come back to the issue of resonance and bond lengths. Yes?
Why couldn't you have all 3 oxygen with double bonds?
So if you go with all 3 with double bonds, so if we're going to come back to molecules that look like bromate and come back to this issue, again, let's look at a slightly different issue with some molecules that don't quite that don't satisfy the octet rule for the other issue where they have too few electrons, like BF3. So BF3, boron has 3 valence electrons, fluorine 3 times 7, 24 electrons. So if we use our usual rule, 3 fluorines on boron, lone pair for the fluorines, that's a total of 24 electrons. So we have none left over. So the rule that we don't satisfy the octet of the central atom with lone pairs is a really good rule to pay attention to here, because you may want to do this, but we don't do that. We don't have electrons available to throw 2 electrons onto boron. So we don't have those electrons available for boron. So boron is deficient of an octet. Now at this point what we might wonder is, do we have some kind of charge to pull electrons in to make a double bond? Like the formal charge of boron here would be 3 for a 0 charge, and it's surrounded by 3 valence electrons. So it has a net 0 formal charge. The fluorines have a 0 formal charge. Okay, now if you think of what the fluorines are really going to do to these bonds, what does fluorine probably do? Fluorine probably pulls electrons away from boron because it's more electronegative and actually picks up a partial negative charge. And of course, if you do quantum mechanical calculations and check the charges, they're all negative in the case of this compound. Now, the textbook does wonder, or does propose, well, what if we make a double bond? So what if you take one of these electron pairs here and make a double bond? So what if we have a Lewis structure that looks like boron, double bonded fluorine. Fluorine's lost a lone pair to make that double bond. So our count of electrons is still correct with 24 total electrons distributed. But then this structure here ends up putting a negative formal charge on the boron because it's now 3 minus 4. Boron's picked up an extra electron. Fluorine has lost an electron and gone to positive. Okay, now this seems really silly, right? Because fluorine's going positive and boron's going negative. That goes against their electronegativities. So it doesn't make much sense that the real molecule would ever make a double bond in this case here. So the formal charge rule would actually follow that we're not going to maximize formal charges essentially at any point. So we never maximize formal charges to satisfy an octet rule. So maximizing formal charges is just something that we're never going to do. Now minimizing formal charges to expand an octet is a tricky issue. So like in the case of bromate on the previous example, we were actually doing something the opposite. We were minimizing formal charges, not maximizing. So we never increase the magnitudes of formal charge with multiple bonds. That doesn't lead to a structure that makes physical sense. The real atoms of fluorine should be negatively charged with some small partial charge. In fact, boron's electronegativity is really low. So it's almost boron 3 plus, F minus. This is almost an ionic compound. Like if we said aluminum fluoride, you would probably say, well, it's just aluminum 3 plus, F3 minus. BF3 is just somewhere in between that and a covalent compound with the equal sharing of electrons. So boron's deficient of an octet, that's okay. So we're not going to satisfy the octet rule in BF3 because doing so would have led to maximizing the magnitudes of formal charge, which does not make physical sense to do so. So now if we contrast that with carbonate ion actually looks a bit like BF3 in that they have the same electron count. So it's 4 plus 3 times 6 plus 2. And so that's 18 plus 6, that's 24, just like BF3. So central carbon, outer atoms, octets. Okay, and then we could stop and calculate formal charges. Oxygen, 6 minus 7, so these are minus formal charges. So we're just binding with central atoms, single bonding, filling lone pairs with the non-central atoms, calculating formal charges, and we notice the positive charge on carbon. So that positive charge on carbon should then pull in a negatively charged electron to make that double bond. So the charge is there to pull in the electrons to make that double bond. So we make a double bond. formal charge magnitudes drop to 0 and 0, but we still have minus and minus for the other two oxygens. Okay, so this would be one of three Lewis structures that are all equally valid for carbonate ions. Now, we could actually keep going. You can say, well, what are the other two? We're like making sure that we see, well, we could have written the double bond with any of these oxygens. And what we end up with is a different Lewis structure, but it's equivalent in what it represents. Like it's equivalent in energy, it's equivalent in like the stability, if you will. Like whatever the relative energy is of this structure is exactly the same as here, exactly the same as there. So this is the case of having what we would call equivalent yet different Lewis structures. Okay, so there's a bit of an idea here that a Lewis structure isn't the real molecule. Like it's a representation, it's a model. It's trying to help us understand what the real molecule might look like in terms of its structure. So a few things with the Lewis structure is that it's just a model, it's not the real molecule. We're trying to understand real molecules through the idea of using Lewis structures. Two, the actual arrangement of the atoms is not even three-dimensionally accurate. So like when we do draw a Lewis structure, we're not trying yet to think about where the atoms actually are relative to each other. For example, carbonate probably doesn't have two linear oxygens and then a 90-degree oxygen. We're going to see in the next chapter, we're going to end up with perfect 120-degree bond angles in a geometry called trigonal planar for something like carbonate. Or like when we draw methane, CH4, we easily draw a Lewis structure that looks like this, that methane really isn't a flat planar molecule. It ends up being like tetrahedral and has a three-dimensional shape associated with it. So we have to come back to an idea of three-dimensional shape in chapter 9. So first things first, Lewis structures aren't meant to necessarily show you the real shape of the molecule. What they're trying to get us to do is to think about, or do we have single bonds connecting atoms, double bonds? Do we have this idea of resonance? What resonance is when you have the case of equivalent structures, that this extra bond, that double bond, is going to spread itself out at all times across the molecule. What we're going to end up with is the composite representation of those three equivalent yet different Lewis structures. The composite, the average of those, is going to be your best approximation of what the real molecule looks like. So in other words, the real molecule of carbonate will look more like three single bonds to oxygen, and then with an extra bond spreading across those three connections at any given moment. So it's like what we're taking is the 1, 2, 3, 4 bonding pairs of electrons. So we're taking the 4 bonding pairs of electrons and spreading them across the 1, 2, 3 covalent bonds linking those atoms together. So we're taking the 4 divided by 3, 4 bonding pairs of electrons, spreading them across 3 different connections of those atoms. So 4 bonding pairs spread across 3 bonds for like a 4/3 type bond. Meaning that that bond length, if you think of a single bond being longest, double bond being the shortest, it's going to be in length somewhere in between. So a 4/3 bond, if we're looking at a single bond between carbon and oxygen in a different molecule, should be a little bit longer. And if we're thinking about the double bond length in like CO2, should be a little bit shorter. So this 4/3 bond is like a single bond would have a bond order of 1, a double bond would have a bond order of 2. So if we're looking at a few different molecules, like if we're looking at methanol, that this bond here would have a bond order of 1. So for that CO bond, 1 pair of electrons spreading across 1 CO bond. Or like if we have CO2, double bonds here, this bond order would be equal to 2. So a double bond has a bond order of 2. Single bond has a bond order of 1. So BO stands for bond order. And just doubles 2, singles 1, 4/3, somewhere between the two. So we can use this to start thinking about bond lengths so that we can, and remember before I mentioned at the start of the chapter, bond lengths is something we'll talk about towards the second half of this chapter because it gives us like an experimental predictable quantity. So we can sketch some Lewis structures, compare bond orders, and then predict bond length trends, and then maybe go see if our predictions are correct. So it's just something we can use a Lewis structure to help us predict, see if it's correct, gives us a correct trend for the real molecules, in the problem. So it's just a way to come up with a prediction for our model to see if it's correct. Okay, so carbonate should have slightly shorter bonds. There's actually a problem in the recitation activity for this coming week that has you compare like the bond lengths in carbon monoxide, carbon dioxide, methanol, and carbonate ion. Now let's look at sulfate, SO42 minus, kind of come back to this. So 6 for sulfur, 4 times 6 plus 2, that gives us a count of 32 electrons. So central sulfur, oxygens, lone pairs. So this is an example where we'd have to be told, well, do we want the Lewis structure to satisfy the octet rule? Because this structure here satisfies the octet rule. We have minus formal charges for the oxygens, and we have a plus 2 formal charge for sulfur. And then you could also come up with the formal charge rule. So if you want to apply the formal charge rule, which would say minimize the magnitudes of formal charge with multiple bonds, then go to S double bond for 2 of them, single bond for the other. So both structures have 32 electrons. The one on the left side just has 0 formal charges on 2 of the oxygens and a 0 formal charge on that central sulfur. So their formal charges are reduced as low as they can go. We can't do another set of 2 double bonds because then the formal charge on that sulfur would be minus 2, and that would increase its formal charge. So we can decrease formal charges. So the formal charge rule is you decrease the formal charges with multiple bonds, expanding octets. But again, you can only expand the octet, or you only even see these types of compounds exist where that central atom is in the 3rd row or bigger. So we cannot expand an octet for any reason for an atom in the 2nd row. So if we had like nitrogen here and we're thinking about expanding its octet, we actually couldn't do that. Okay, so that actually comes up in this example here. So let's look at a top hat problem. Let me get started on something with nitrate because it kind of ties together what I'm meaning with the 2nd row not able to expand its octet. So for these 2 structures, the problem does say the Lewis structure for which molecule contains a central atom with a lone pair of electrons. So interestingly, that particular question won't depend on this formal charge versus Lewis structure rule. But let's look at nitrate together. Then I'll let you guys do sulfate together and answer the question. So for nitrate, 5 plus 3 times 6 plus 1, 1 for the charge. And so that gives us a total count of 24 electrons, 24 valence electrons. So usual rule, single bonds first. So minus formal charges all the way around, plus 2 formal charge on that central nitrogen, 5 minus 3. So then you make 1 double bond. So you picture, okay, I'm going to take these electrons here, make a double bond. That drops this formal charge to plus 1, this one to 0. So do you do it again? And if so, why? Or if not, why not? Well, we don't do it again because nitrogen's not in the 3rd row or bigger. Nitrogen cannot expand its octet. So for nitrogen, we stop and don't do this structure. So this one would be wrong because nitrogen cannot expand its octet. If we had phosphorus, PO3 minus, if we had phosphorus here, then that would be okay. Then we could use that 2nd double bond, satisfy the formal charge rule, and come up with 2 possible valid Lewis structures. One that's satisfying the octet rule, and another that's satisfying the formal charge rule. In the case of nitrate, we actually would come up with the same answer because nitrogen is not expanding its octet. So the lowest its formal charges can go, and this particular ion would be plus 1 for the nitrogen. Now, a big kicker is that all of the bonds should be equivalent there. All the NO bonds should be the exact same length because of resonance. So whenever you see 1 double bond, 2 singles, exact same atom in all the spots, that double bond should be able to spread itself out, average itself out. So all the bond lengths in nitrate should be equal in length. The NO bonds should all be equal. They're all about 4/3 bond order. So a little bit shorter than a single bond, a little bit longer than a double bond between the N and the O. Now the actual question, let's look at the question. It says the Lewis structure of which molecule contains a central atom with one lone pair of electrons? So the actual question itself wasn't even requiring us to necessarily go through the thought of resonance or to go through the thought of where do we stop in terms of the double bond count. So as soon as we saw that we don't have a lone pair of electrons on nitrate, the answer is no to the particular question being asked. So there's a lot of aspects of Lewis structures. There's, different types of Lewis structures we can write. There's like, where do lone pairs end up? How do we end up with multiple bonds, double bonds? What does resonance mean? There's a lot of different things we can ask about a particular question. This one's actually just asking something relatively simple. So think about sulfate. Try to figure out if it has a lone pair on its central atom or not, so you can answer the question for the second molecule. I was going to ask you guys your favorite candy. I guess I forgot about that. This is at some point today. I guess it's an extra credit question, so you can answer that too. All right, so interestingly, Twix is really high in the running. I'm surprised by that. It seems like weird candy to have as my favorite candy, I don't know. Although I've probably eaten about 5 of those already this Halloween season. My kids don't like the chocolate candy, so I get to eat all of their Reese's Peanut Butter Cups, and see me in a month, I'll be much bigger. So sulfate here, or sulfite ion, ends up with 26 total electrons, single bonding the electrons So going with single bonds first gives 24 electrons, so you see the extra lone pair on sulfur. So the biggest thing to get for sulfide ion is a lone pair on the central oxygen. The single bonds, that would be your Lewis structure answer if you're satisfying the octet rule. And then if you wanted to go with the structure that would satisfy the formal charge rule, we would just take note 6 minus 5 plus formal charge on sulfur minus around for the oxygens. So we'd make one double bond. So we have sulfite with one double bond, two singles if we wanted to satisfy the formal charge rule. So all singles and a lone pair to satisfy the octet rule, and then one double bond if we're minimizing the magnitude of the formal charge. Okay, so now let's look a little bit closer at resonance. So let's start with ozone. So if we're doing a Lewis structure for ozone, 3 atoms, they have to be connected together. So that the only way to connect 3 atoms is one to the next to the next. So there's really no possibilities of how these atoms are connected. If we apply our usual rule, we'd do something like this. Lone pairs on the outer oxygens, count our electrons, 3 times 6, 18 total electrons. We have 16 electrons used, 8 per oxygen. So we have 1 lone pair on oxygen, and then we have a positive charge on oxygen, so we can pull in a double bond. So we pull in 1 double bond, lose it here, and then the formal charge would drop on that O. So we have a formal charge here of 0. This oxygen would have a 6 minus 1, 2, 3, 4, 5 for a positive formal charge, and this oxygen minus. And then for the second row, we're never expanding an octet, so there's never a possibility of making a second double bond. So we're holding still with 1 double bond, 1 single. And so we could have 1 resonance structure. So Lewis structure A would be the one with the double bond between these 2 oxygen atoms, but why wouldn't I make the double bond with the other oxygen? Which of the 2 O's should I make the double bond with? Well, we could make the double bond or recognize that we have the case of 2 equivalent Lewis structures that we could have written. They are different from each other in terms of which of the O's are actually making the double bond. So the real molecule is going to be a composite. So notice that the actual charge accumulation on each of the O's is exactly the same. The bond lengths end up being exactly the same. What ends up happening is that the 2 O's kind of each get an extra half bond in the real molecule. So the real molecule looks nothing like this structure or that structure. It's not a going back and forth. It's like a real-time averaging that the real molecule averages out that extra double bond, that extra set of electrons at all times across all 3 atoms. So what ends up going on is we take the 3 bonding pairs of electrons, so the 3 bonding pairs, and spread them across the 1, 2 covalent bonds for bond orders of about 1 and 1/2, or 3 halves. So the bond length here should be a little bit shorter than an OO single, and then a little bit longer than the OO double. So if we're thinking of the bond lengths for like a molecule of oxygen compared to, say, hydrogen peroxide, hydrogen peroxide has that O2 single bond. So the bond length here in the peroxide should be longer than the bond length in ozone, longer than the bond length in O2. So this would be comparing the oxygen-oxygen bond lengths and those molecules. So peroxide the longest, single bond. Ozone in the middle, 3 halves bonds, and then double bonds, bond orders of 2 in the case of O2. So one of the big keys with resonance is it's not an A and B going back and forth really fast. It's a real-time averaging. Look at nitrate. With nitrate ion, this is actually, these pictures come from chapter 9, but I think it's helpful to see them here in chapter 8. So in the case of nitrate, we saw this earlier, we ended up with a double bond, 2 singles for one of the Lewis structures, minus, minus. So when you look at one of the resonance structures, or one of the Lewis structures where they're equivalent, so there's 3 different possible resonance structures for nitrate ion. If you think of the actual bonding orbitals that make up that double bond, this is what we'd call the localized bond. That's like trying to picture the bond being localized between just those 2 atoms. What ends up happening is that the 2 other oxygens have an orbital pointing the exact same direction that allows for like a simultaneous overlap. So you end up with what's called a delocalized orbital. So you end up with one molecular orbital where all 4 atoms in this molecule participate into putting that extra pair of electrons into an orbital where they spread out across the molecule at all times. So it's not this structure in equilibrium with it being in the other position, equilibrium with the other oxygen getting the double. It's a real-time 2 electrons being in one delocalized orbital. So the localized orbital, this is just not possible. Like, it's not what the real molecule would look like. You would never see a localized orbital in something like nitrate. Or in the case of any molecules where they have equivalent, yet different Lewis structures, you get the real-time averaging because one orbital shares those electrons at any given moment. So delocalized bonding occurs in these molecules. You can see it with some structures we'll look at and see in chapter 9 and see maybe where it is that the actual orbitals that come into these pictures are coming from. We'll get into that in chapter 9. But I just want us to see that there's an orbital that takes that extra electron pair so that each of the bonds ends up being that 4/3 bond order at all times in the molecule. So the bonds here, all the same length. So that's like one of the, a common test question would be like nitrate ion. Which statement is true? One bond is shorter than the other two. Two bonds are longer than the other one. All 3 bonds are the same length. All 3 bonds in nitrate are the exact same length. This comes up in an organic molecule of benzene. So benzene is a hexagonal ring, carbon atoms. Sometimes you can draw it with double bonds here. We have hydrogens. Now the key is, if you notice where the double bonds are, they could shift over. And we could end up with what looks like the exact same structure, but where the double bonds are now here, here, and here. Now in terms of predicting the Lewis structure of something like C6H6, I don't think we're going to get into the business of giving you an organic formula and expecting you to reproduce a Lewis structure for something big like an organic molecule. That's kind of what OChem 25, 10, and 20 are for, so you'll learn all about OChem molecules and structures there. But what I want us to see is that when we're picturing the double bonds being in this position versus this position here, that these molecules also fit the category of being 2 different yet equivalent Lewis structures. Delocalized bonding would not occur in these molecules. Localized bonding would not occur. We would never really have a true double and a true single bond in a real molecule of benzene. Instead, what we'd have is all of those double bonds spreading across the real molecule through delocalized bonds. So we would not have real localized bonding in a real molecule of benzene, only the delocalized bonding. Now, if we're counting the bond type here that we'd expect, we have, like if we start counting the bonds, let me use a different color. So we'd have 1 bond, 2, 3, 4, 5, 6 carbon-carbon bonds, right? So we have C6H6. We have 6 actual covalent bonds. And then we have a total of 2, 4, 6, or excuse me, we want to count pairs, not individual electrons. So we have 1 pair, 2 pair, 3, and then 4, 5, 6, 7, 8, 9. So we have 9 pairs of electrons. So we have like 9 single lines and then, or 6 single lines and then the 3 extra double bonds. So we have 9 bonding pairs. So 9 lines connecting the carbon atoms. So we have 3 doubles, 3 singles, and then across the 6 actual covalent bonds. So the bond type here would be about 3/2 bonds. So again, a little bit shorter than single bonds, a little bit longer than carbon-carbon double bonds. Okay, so think about the Lewis structures of the molecules below, NO-, NO2-, NO3-, and try to rank them in terms of their nitrogen-oxygen bond distances. I had a question I opened and that was out of order, but that just popped up. But the just look at the NO bond length question first. right, guys, let's take a closer look here. So for NO minus, 5 plus 6 plus 1. So that's 12, plus 1. So that's 12 electrons total. So that's going to look like O2 with a double bond. So not NO double bond. So that's 2, 4, 6, 8, 10, 12 electrons, giving both their octet. 0 formal charge on O, minus on N. So that's our best Lewis structure. The key there is seeing the double bond. We've seen nitrate has a double bond, 2 singles in one of the Lewis structures. So the molecule is going to balance out the 4 bonding pairs across the 3 bonds for like a 4/3 type bond. In the case of nitrite ion, NO2 minus, we have 3 pairs of electrons to the double and the single spreading across the 2 connections of the NO. So 1 bond, 2 bond. So 3 halves. Now, which bond's the shortest, the double or the nitrate? So will the double bond be shorter, or will the 4/3 bond be shorter? So the more bonding pairs, the more glue you have to hold the nuclei together. So NO should be the shortest. So 1 should be the shortest because it has the most bonding electrons. Nitrate has the fewest bonding electrons. So its bond order is 1.33, 1.50. Nitrate has the fewest bonding electrons. Nitrite has the intermediate in the middle. Okay, so nitrate should be the longest. Here, nitrite in the middle. Okay, so let's review a few other generalities or cases where we see octet rule violations and figure out how we write the Lewis structures. So in the case of something like OH, where we don't have a minus charge, I never give you guys time to say IO. It's kind of essential. We don't have time for IO. But so we have an odd electron count. So obviously in a molecule with an odd electron count, we're going to have a hard time satisfying the octet rule for both atoms. So there's really no other opportunity or no other Lewis structure we can really come up with for OH. We have a single bond, can't really go fewer than a single bond. And then the formal charge on oxygen would be 6 minus 1, 2, 3, 4, 5, 6. So a 0 formal charge. So both atoms have a 0 formal charge in the hydroxyl radical. So that's hydroxyl radical instead of hydroxide ion. What about the case of NO? So NO without the minus charge was pretty easy because it just looked like O2. But what about the case of NO where we have an odd count of 11 electrons? Well, if we had 10 electrons, we could go with a triple bond. But we have too many electrons to go with a triple bond, so we're going to be still stuck with a double bond. So it's also kind of like we're kicking an electron off of the NO minus. So it's like either we can kick an electron off of the oxygen or off of the nitrogen. So these are the 2 Lewis structures you might come up with for NO, for nitrogen monoxide. For nitrogen monoxide, we might then compare their formal charges. So when I have 2 Lewis structures that I can write, both of them seem to be almost as good as each other, like which one's better, I might go to formal charges and see that the compound here, or that this Lewis structure would have a 6 minus 6 for O, 5 minus 5 for N, 0 formal charges for both. Compared to this Lewis structure here, formal charge of oxygen positive, 6 minus 5, and then 5 minus 6 for nitrogen, for minus. So I don't want to maximize the formal charge. I don't want to put a positive formal charge on the lesser electronegative atom either. So this seems bad for a lot of reasons. So this would be our best Lewis structure for nitrogen monoxide. Now CLO seems very similar. Or like when we start sketching it out, CLO has 7 plus 6, 13 electrons overall. So we have Cl. Oh, we don't have enough. We don't have too few electrons for a double bond, so we're stuck with the single, and then either filling an octet on oxygen and then not chlorine, or the other way around, filling chlorine's octet and then leaving oxygen's deficient. So which one of these 2 Lewis structures is better? This is a tough one. What we have to do is think about minimizing. So when I have 2 Lewis structures where I can't satisfy the octet rule in both, I'm going to choose the one that minimizes the magnitudes of formal charge. So I want the lowest possible formal charges. This structure here, chlorine should have 7, 1, 2, 3, 4, 5, 6. That's plus. Oxygen's formal charge would be minus 1, 6 minus 7. Now over here, 7 minus 7 for chlorine, 0 formal charge. Oxygen, 6 minus 1, 2, 3, 4, 5, 6 for also 0. So this is actually better. Now at first glance you go, but I thought we liked O minus. I thought having oxygen with a minus formal charge made sense. It's more electronegative, it has a negative charge. What's so bad with this structure? Well, the answer is the formal charge magnitudes are greater. If we have two equivalent Lewis structures that we're choosing between, we want to choose the one that minimizes the magnitudes of formal charge, if all else is equal. So all else is equal, like both compounds are breaking the octet rule equally, just one atom is violating the octet rule. So we're choosing the atom or the Lewis structure that minimizes the magnitudes of formal charge as the better Lewis structure. Now we saw before, we had BF3 has fewer electrons in an octet. Carbonate looked like the same, but it ends up picking up an octet on the central atom because it has a positive charge to draw on a double bond, unlike BF3. So BF3 is perfectly happy. Violating the octet rule, carbonate actually satisfies the octet rule. So we can satisfy the octet rule with the double bond that we can't satisfy BF3s with just because the charge of carbon is greater. It can actually hold and make that extra double bond. Now we have some octet rule exceptions on the other side for where you can have more electrons in an octet. Some of these cases are we just kind of have to. You know, it's like if you take a look at PF5, 7 times 5 for the fluorines plus 5 for phosphorus has a total of 40 valence electrons. That's just phosphorus with 5 fluorines, all satisfying their octets with lone pairs. So I'm not going to write the lone pairs, but that would just be 5 fluorines times 8 each. So no electrons left over for lone pairs on phosphorus, but still 5 single bonds. So this molecule exists while it expands the octet of the central phosphorus. There's like no choice around the Lewis structure violating the octet rule. But of course, the fluorines are going to pull electrons off the phosphorus because they're partially negatively charged. We're not going to form this compound with like hydrogen. Like pH5 isn't a stable molecule that you're going to put into a bottle. But PF5 or PCl5, these compounds exist because the outer atoms can pull the electrons off the central so that the atom really doesn't have to violate or expand its octet. And then there's like SF4, ends up having an extra lone pair on sulfur. I'll leave that example for later. PO4 3- looks kind of like sulfate, where we're stuck with possibly expanding an octet to minimize magnitudes of formal charge, which we can do, but also understand that it's also sometimes equivalent or acceptable to not expand the octet with double bonds. I wanted to do at least 1 or 2 more examples off this page here. Carbon monoxide is actually a pretty easy Lewis structure, 4 plus 6. This is probably not too far out there to come up with a Lewis structure like N2 with a triple bond. What I wanted to point out for carbon monoxide, though, is that notice that the formal charges kind of revert here, where carbon ends up being negative. It has a -1 formal charge, 4 minus 5. Oxygen's 6 minus 5 for a positive formal charge. Now, there's no other way we can satisfy the octet rule for both atoms with any other Lewis structure. So that's like the only possible Lewis structure for this molecule. Now, remember, you can still think about how oxygen's more or less negative. The triple bond's going to shade itself more closely towards the O. So we probably would expect oxygen not quite to be +1 in charge, but it still ends up being positive. The carbon still ends up being negatively charged. If you breathe in carbon monoxide, it's actually the carbon that attaches itself to hemoglobin in your body and actually doesn't irreversibly remove itself. So if you breathe in carbon monoxide, it's the carbon that attaches to your hemoglobin, and carbon attaches irreversibly to hemoglobin. When you breathe in oxygen, it's the O atom of oxygen that attaches to hemoglobin, which irreversibly or reversibly adds. So if you breathe in oxygen, it can be removed from hemoglobin. Unfortunately, carbon monoxide can't. Electronic structure puts that negative formal charge on the carbon atom. Okay, so I'll leave these examples for some other time, but we'll stop here for today. We're moving into chapter 9 on Thursday. So see you guys next time.